Okay, so we're very happy to have Luca Delacrétaz from Chicago, and he will tell us how to properly bosonize a Fermi surface. Take it away.
Thank you, Theo, for the introduction and for the invitation to come here. It's my first time visiting. I'm very happy to get to see the place and talk to people. Fermi surfaces probably aren't what most hydrogen physicists think of on a daily basis. So I just wanted to kind of maybe spend at least a slide explaining to you why it's the coolest thing you could be thinking about. And also, more seriously, why I think it is a kind of frontier even in formal quantum field theory research. And what's nice about this frontier is that it does have a lot of experimental applications in condensed matter physics. So it's a kind of nice place to devote some energy to. So really what so the simplest way to get a Fermi surface is to just have a bunch of free fermions. By Pauli's exclusion principle, if you add fermions to your system, they'll have to occupy higher and higher momentum states. And in the thermodynamic limit, if you take the number of fermions to infinity as well, you'll end up with a smooth Fermi surface that looks like this. And what's really fascinating about these states, these Fermi surface states, is that they're extremely gapless. They have a whole collection of excitations where you remove a fermion just below the Fermi surface and put it just above the Fermi surface somewhere else. That costs essentially zero energy, but is a finite wave vector excitation. Okay, so if you kind of plotted a spectral density in such a system, you would have this whole continuum of states that you can excite. Okay, that at finite wave vector, but at essentially zero frequency. Just to contrast this with what we're used to seeing in particle physics, let me kind of first just consider a free scalar, free massless scalar. Its spectral density would just have a pole where the scalar lives. Now I could add interactions, of course, and get a particle hole, a kind of multi-particle continuum. I could also add interactions on the Fermi surface side that would also lead to a continuum here. But you're never going to get this huge gaplessness, right? All these essentially zero energy states at finite wave vectors. This is really something unique in these Fermi surface states. I think it really kind of underlies this extreme gaplessness underlies all the rich phenomena that come out of Fermi surfaces, but also why they're pretty challenging to kind of address with conventional quantum field theory tools, and why we need to develop some new ones. Right, and when of course on top of this you add strong interactions, then in this backdrop of extreme gaplessness plus strong interactions, a lot of all hell breaks loose, and there are very few controlled approaches to understand what's going on. So that's kind of the arena where we will be. Now, in most contexts, interacting Fermi surfaces are described by a very successful and very old theory, Fermi liquid theory, Landau's Fermi liquid theory. It's almost 100 years old and has had countless successes. But I think even within the context of Fermi liquid theory, there's some questions that reveal the fact that we don't really have a full understanding of what's going on. And I listed a few questions that are on my mind, but that's not an exhaustive list. So one of them is the existence of protected observables in Fermi liquids. So as you might know from Fermi liquid theory, the Fermi liquids you can think of it as an effective field theory that has a whole tower of marginal interactions, which is pretty unusual from the perspective of effective field theories. These marginal interactions are called Landau parameters. And so if you compute an observable in Fermi liquid theory, it's going to depend on, at leading order, it's going to depend on all these marginal interactions, on all these Landau parameters. And generically they do. But there's a handful of observables where, for some reason, all of these non-universal Wilsonian coefficients drop out of the answer. And the observable only depends on the kind of geometry of the Fermi surface in a seemingly universal way. One famous one is the entanglement entropy of a Fermi liquid, which is also interesting in its own right, because Fermi liquids are kind of the most entangled ground states that occur naturally in nature. They violate the area law here with the 2+1D version of entanglement. But there's also examples that are a little more experimentally accessible. For example, this connectivity is a specific limit of the current two-point function that simplifies and has a universal geometric form. And so our current, our understanding of these observables is that we compute them in Fermi liquid theory with all the Landau parameters, and you see at the end of a long calculation that they drop out. And the answer is very simple. but it suggests that there might be some kind of, maybe algebraic or symmetry reason for all of this. There's also situations where Fermi surfaces emerge from, maybe the fermions are not the microscopic degrees of freedom you had, and understanding how UVIR type constraints in this context play out would be very interesting. And maybe a kind of, this last point, kind of more precision physics type point. There are, non-analytic corrections, power law corrections to Fermi liquid theory, but they're extremely hard to compute. And you might want to systematize this type of work. But of course, the elephant in the room and the main motivation to study Fermi liquids, I think, nowadays, or to understand Fermi liquids to depth, is the existence of non-Fermi liquids. So we know that there are relevant deformations of Fermi liquids. For example, if you couple a Fermi liquids to a gauge field, that should lead to something. Okay, that's not going to be a Fermi liquid. And in some situations, it's believed to lead to new fixed points, which is potentially universal, has some universal scaling of observables. And in these situations, even very basic questions are not known. So for example, we expect some, if there's a scaling invariant fixed point, we expect some scaling of observables. It's of course not Lorentz invariant. There's a very old approximation which gives a dynamic critical exponent z equals 3 from 50 years ago. And to this day, we don't even know if it's exactly 3 or approximately 3. So there's even very basic questions that we don't know the answer to. So okay, I'm not being completely fair to my colleagues in this pursuit. There has been a lot of progress, but I think it's safe to say that there's a lot of open questions. And so the hope that I'm going to pursue is that some form of Bosonization can help address some of these problems. So I won't solve non-Fermi liquids today, but I will tell you about progress in understanding Fermi liquids and some of the puzzles I put earlier from this different kind of perspective. So, the motivation for why Bosonization might help is that, of course, in one dimension, it is a very powerful framework. Here, just to give you an example, I kind of been showing probably the simplest Bosonization duality. So on one side, we have a free Dirac fermion, and on the other side, a compact scalar at some radius. Now, both sides are free, so the very simple duality, and both sides look equally simple. But for some questions, the bosonic side is preferable. For example, if you're interested in correlation functions of the current or the density, the U1 charge density, on the boson side, it's linear in the field, the boson field. And so, for example, its 2-point function will be given by this loop diagram on the fermion side, but on the boson side, it's just going to be the propagator of the scalar, which you can just you can just write the answer by staring at the action. But now if you start asking more complicated questions, like let's say you want to compute the 14 connected point function of densities in this theory, on the fermion side, you would have to compute, even though it's a free fermion, you'd have to compute this loop with 14 insertions. You'd have to symmetrize over all possible ways to connect these insertions. And what you'd find is that after summing over these different diagrams and performing the integral, the answer is 0. So the things cancel, but not before. Whereas on the boson side, it's immediately obvious that the answer is 0 because it's a Gaussian theory, and we have the density is linear in the field. So we see a kind of advantage to the bosonic description, which kind of carries over when we start complicating the problem. Let's say we add interactions. So one famous example is the Schwinger model. I guess in this room I have to, it's good to mention it, namely QED in 1 + 1 dimension, which of course we've probably all solved it several times in our life, but if you look at it for the first time, it looks like a complicated problem. There's a relevant interaction. There's no small parameter. You might think there's no way to solve it, but in the Bosonized description, the solution is completely obvious. The entire action is Gaussian. You see that the fermion is the photon is. So so that's kind of unfortunately the world is not as simple as 1 + 1 d Dirac fermions, but that's kind of some motivation for the hopes for Bosonization. So there have been efforts already for quite some time, for several decades, in inspired by this 1 + 1 d Bosonization, to describe Fermi surfaces in this way. And we'll, I'll explain how one gets to an action like this in a bit, but for now I'll just kind of tell you what these actions look like. So what these people came up with is a bosonized description of a Fermi liquid, a Fermi surface. And roughly what it is a chiral boson. So that this, you can kind of recognize the action of a chiral boson, which is propagating away from the Fermi surface. Okay. And so, as in bosonization in 1+1D, you can think of this boson as a particle hole pair, which has this description. So we have basically a sum of decoupled chiral bosons on the Fermi surface, and then you can add interactions. These would be interactions in the fermion description, which correspond to Landau parameters that couple different angles. So this is we'll get to how one derives such a description, but some things that it does already nicely is that it will nicely capture correlation functions of the density operator. So the density operator now is not just gratified, but it's the density operator doesn't depend on angle; it just depends on space and time. So it's going to be an integral over. Right, there's this funny thing about this action, which is that it lives in space-time and in this extra dimension. Okay, we're going to come back to that as well. It's a little bit unusual. So this is the density operator. And let's say we want to compute the density 2-point function in a Fermi liquid, or kind of a cast of free fermions here for now. So on the fermion side, you would compute this loop. And now, as I mentioned before, this looks very different, right? It doesn't look like a pole, like in 1D. Now you have a whole continuum on the fermion side from this loop. Okay. How are you going to get this whole continuum from a tree-level diagram? Right, that shouldn't happen. Well, the point is that on the boson side, it's a tree-level diagram, but there's a continuum of fields. Okay, there's a field labeled by theta, and so the integral over theta kind of replaces one of the three integrals in the loop, roughly speaking. And so you see if you just integrate this propagator, parallel boson propagator, that what gives you this branch cut. Okay, so that's something that it does nicely. One thing we kind of explored in past work is that, so you might ask, okay, what about nonlinear response? What about, the analog of what I discussed earlier, connected 14-point functions, or maybe just 3-point functions to make things simpler. So those actually turn out no longer to be zero, okay, in higher dimensions. But interestingly, there's still a remnant of this cancellation we saw earlier in 1+1Z for the Dirac fermion in the form of partial cancellations in these loops. So if you compute this diagram and then the corresponding one with arrows going the other way, and so sum the two and perform some integrals, there's a partial cancellation and the final answer is smaller than what you expect. The scaling is smaller than what you expect. This turns out to be immediate in bosonization. So as we'll see, there's this kind of action has nonlinear terms as well that are inevitable. But these nonlinear terms are gradient suppressed, they're irrelevant. And so their irrelevance exactly tells you how suppressed this 3-point function is compared to, and higher point functions are compared to what you might have expected. So these are some things that kind of, I would say partial successes of this bosonized description of Fermi surfaces. But one thing you might notice is that these are all classical predictions on the boson side. Okay, these are tree-level diagrams, which are reproducing loops on the fermion side. What I'd like to do today is try to understand this type of field theory as a genuine quantum field theory. And there's several things that make this not at all obvious. Okay, there's several very strange and fishy things going on in this field theory. So the first, as we discussed, is that the field doesn't just depend on space-time, it depends on a part of phase space. It lives on the Fermi surface. So you might worry that it's really it should be some kind of non-commutative field theory. Part of it depends on phase space. Another concern is that if you wanted to just start quantizing this theory, as we saw, only gradients in a specific direction away from the Fermi surface cost energy. So the field phi was only propagating away from the Fermi surface, right? Here it is, kinetic term. Only gradients away from the Fermi surface cost energy. And so if there's this completely soft direction, gradients along the Fermi surface are completely unsuppressed. Okay. So this phi won't have a nice Fock space description. And finally, and all these points are kind of related, as we'll see. there naively seems to be a huge overcounting of modes if you view phi as the fundamental, if you view these particle hole pairs as the fundamental degrees of freedom. Okay, because right, the kind of hope in bosonization is of course that the scalar, this bosonized description is weakly coupled, otherwise it wouldn't be extremely useful. But if we viewed every phi as a kind of weakly coupled harmonic oscillator, that would be a huge overcounting, right? Because we know that in some limits, Fermi liquids just become free fermions, right? That's a reasonable Fermi liquid, in which case the fermions are weakly coupled harmonic oscillators. And if I count pairs of fermions, there are way more pairs of fermions than there are fermions, right? So it seems like I would get completely wrong answers if I compute any observable that measures the number of degrees of freedom. So today I'll solve all of these issues and try to make sense of this field theory as a quantum field theory.
Is phi compact at this stage, or do people?
So far, yeah. So I'll come back to that. It'll make more sense in the quantum description. But that question is kind of related to. I think there probably wouldn't you wouldn't ask this question in a classical field theory. Probably there wouldn't be. Yeah. But I'll come back to that, and eventually the answer will be yes. But we'll see. Okay, so those are kind of the formal questions I want to solve, and maybe to make this pragmatic, maybe so something you might want to understand is how to. So there's this description of Fermi liquids we had. You might want to know how to capture deformations of Fermi surfaces of Fermi liquids, either relevant or irrelevant. So this is certainly necessary to understand how to study non-Fermi liquids, which will involve a relevant deformation. But the one kind of concrete goal for today will be to capture irrelevant corrections in Fermi liquid theory. So power law corrections proposed in a Fermi liquid. In 1D, in 1 plus 1D, I should say it's kind of very well understood how that works. Let's say you don't have exactly a Dirac fermion, 1 plus 1D, but you have a fermion whose dispersion has some k dependence that's not exactly linear, maybe not exactly a relativistic fermion. This will map, so that it's still a free fermion, but with some higher derivative corrections of the action. This will map to a very specific operator in the Bosonized description. And now if you wanted to compute, corrections to observables from this deformation, you could do it. Obviously, it would be easier to do it on the fermion side since it's still free, but you could also do it on the boson side. And you would get these loop corrections to observables, which are actually quite interesting. They have this on-shell singularity. They blow up near on shell and they can't be resummed. It's related to the opening of a particle hole continuum in 1 plus 1D. But it's otherwise kind of very well understood. So we'd like to try to understand how to do that, how to capture systematically corrections to observables. What we'll see in higher dimensions is that some corrections are very similar to 1D in that they come from things like say the dispersion relation of the fermion is not exactly linear. But there's also some corrections that are really inevitable and come from the shape of the Fermi surface, the fact that you have an extended Fermi surface and that it curves, it's not exactly flat. So that will be, okay. And then at the end of the talk, I'll turn to actual interacting Fermi liquids, where we'll try to understand leading non-analytic corrections there. And there we'll be actually able to make new predictions on the leading non-analytic corrections to various observables in a Fermi liquid. These are things that are extremely hard to compute on the fermion side because of many cancellations that you have to do a lot of work to get these zeros on the fermion side. But we'll be able to kind of shortcut to get the final scaling result. So, okay, so that's where we're going. I should say all of this is based on work with my excellent student, Han Chen. And so this is the plan for today. So as a warm-up, we'll start by thinking about flat Fermi surfaces. This is actually much simpler because effectively, as you'll see, it's a one-dimensional problem. And we know how to 1 plus 1 dimensional problem. And we know how to do bosonization in 1 plus 1D. Then I'll present to you this cojoint orbit method that we developed to build these Fermi liquid effective field theories, which will allow us to kind of easily generalize and finally study general Fermi surfaces. So that's the general plan. Are there questions before we dive into it? No questions. So let's start with flat Fermi surfaces. So let's consider the following problem. Let's say you have a collection of chiral Weyl fermions, right, moving Weyl fermions. Let me put them in an array of wires. Okay, so they're all just decoupled. And so if I had to draw the momentum space picture, right, this would correspond to a Fermi surface. Left is filled. This is my Fermi surface. And so here this is kind of in the continuum limit, right? N goes to infinity, you get a smooth Fermi surface. That is a circle, right, with periodic boundary conditions. This is, I guess, the Brie one. So, this looks like a extended Fermi surface, but of course it's really a 1+1D problem. So we should be able to solve anything we want. And in fact, there's many ways to bosonize this description. Let's see. So one thing you can certainly do is bosonize each wire individually. Okay, so this will give you a single chiral boson labeled by the wire. This is basically a chiral version of the duality I showed earlier, just the right moving boson. Notice that the boson has a single wire index. Okay, I really took every wire and bosonized it individually. But one thing this description doesn't have, the starting point had a UN symmetry, right, that rotates the fermions among themselves. That UN symmetry is not fully manifest, right? This has this smaller symmetry. So this also has UN symmetry, but it's not manifest. There's another description that keeps this UN symmetry manifest. It's the non-abelian bosonization of this model, namely the description in terms of a UN level 1 WZW CFT, okay, which has this form here. Again, I'm writing the chiral version, so it looks a little bit funny. That's just the right moving sector of the UN level 1 WZW model. So these are three descriptions of exactly the same thing, completely equivalent, and they make various things more or less manifest. But I'd like to claim that this last description actually looks a lot like Fermi surface bosonization. Okay? And you should think of a Fermi surface bosonization as being some kind of non-abelian bosonization. Let me explain why. So in this last description, the boson field really is a matrix. Okay, it's an n by n matrix. Here it just had one wire index. Here basically it has two wire indices. So it's kind of, I guess you could say it's bilocal in the fermions, right? So there's some dictionary between fermion bilinears and these operators. If I just kind of naively expand the matrix G in UN, I would get this type of relation. Okay? This is very similar to Fermi surface bosonization. So remember, in Fermi surface bosonization, the field depends on space-time and on the Fermi surface parameter. It was an angle before, now it would just be Py. Okay? Which is essentially the same thing, or really the Fourier transform, right? This is space. Here I have two coordinates. So there's some Fourier transform going on, but the important thing is that if you have n wires, you have n squared of these bosons. Okay, this is this naive overcounting of degrees of freedom at Fermi surface bosonization. So why isn't this a crazy overcounting of degrees of freedom? Well, the point is that the bosons are strongly coupled, but they have strongly coupled but solvable dynamics. And in fact, the central charge of the UN level 1 of DW model is exactly what it should be to describe these n Weyl fermions. Okay, the phis are not weakly coupled. If the phis were weakly coupled, this would be n squared. For example, if you take k to infinity, they're weakly coupled. But when k equals 1, you get the right number of terms. So that's already giving a hint as to how how this naive overcounting of degrees of freedom will work out for general Fermi. So we're going to try to use this to understand more general Fermi surfaces. Are there any questions?
Is some form of locality in the y direction we discussed up to now?
Yeah, so here it didn't really play a role. So I should say, in practice, this is a bit of an artificial model, right? If you were actually considering a realistic wire setup, you would probably be interested in adding hopping terms, which would break or at least modify the UN symmetry. And you would probably want them to be local. So it's true. So obviously all of these dualities are very old and well understood. But the important thing I want to do here is give a spatial interpretation to this n. That's something that will kind of stay with us in some way.
We're making an open reliable break the symmetry, right? Adding hopping terms, so on, break
Well, actually, if you just, it depends what terms. So if you add hopping terms like this, here I wasn't adding this to the Hamiltonian, right? But if I add this to the action, there's actually still a UN symmetry, which is not too surprising, right? It's still free fermions. But indeed, if you're more general and add also nonlinear terms from interactions that involve simple wires, you would eventually break the UN. Yeah, I should say that there will be a bunch of UNs in this talk. They won't be a symmetry that I enforce. There will be a good guiding principle to kind of construct the action, but I will want to break it. That's right. So deformations there will be deformations of the model that break the UN. But the starting point will have it'll be useful to have the UN as a starting point. Any other questions?
Maybe you'll explain this later, but the scenario where I have n individually bosonizing each of the n. That also has n number of degrees of freedom.
Yeah.
So is there a reason why you're
picking the more complicated one? Yeah, no, that's a very good question. I basically want to make a connection to this conventional Fermi surface bosonization description, which has more degrees of freedom, because that has very nice connections to semi-classics, and as we'll see in a bit. But right, it has an appeal of its own. It's true that you might say, what's the advantage of this? It's strongly coupled. It is solvable, but still it's strongly coupled. Maybe one formal comment is that there's more operators you can represent locally in this description. So for example, this fermion bilinear, strictly speaking, has strings on both, right? If you bosonize each, so it's a little bit nicer in this description. But there's other advantages from my perspective, which will become clear soon. The fact that it connects nicely to the space picture, as I'll explain. So right, so maybe so to kind of generalize to arbitrary Fermi surfaces and understand this connection to semi-classics, let me tell you a little bit about this coadron orbit method to obtain these effective actions. So the point of these coadron orbit methods is precisely it kind of addresses this question. It really will make the semi-classical limit of Fermi liquids manifest, as we'll see the degree of freedom is a distribution function, like you might have in kinetic theory or the Boltzmann equation. And we'll have some action that I'll explain in a bit, which in various limits reduces to essentially, all these previously known bosonizations, 1 plus 1 debosonization, or other Fermi surface bosonizations and so on. So let's see how it works. So the degree of freedom is really just going to be a fermion bilinear. Okay. And here what I'm doing, this is called the Wigner transform. I'm Fourier transforming the relative coordinate between the two fermions. So this defines an f, sometimes called a distribution function, which lives in phase space, so x and p. Now this operator, its Heisenberg equation. Let's obtain its Heisenberg equation of motion for an arbitrary but free fermion Hamiltonian. So I'm not even considering a local Hamiltonian here. Let me later we'll obviously impose some things on the Hamiltonian. I just want to kind of see the general structure of the equation of motion of this object. So if you compute the commutator of this f with an arbitrary local Hamiltonian that I wrote, that one can write in this way, it turns out to have this form. The commutator essentially becomes basically a Poisson bracket of these two functions. It's not exactly a Poisson bracket. It's called a Moyal bracket. It has this sign, but in the semi-classical limit, if you expand gradients, it becomes the Poisson bracket. So this is an algebra that has many names: GMT, W infinity, and so on. So this is the equation of motion of a fermion bilinear in an arbitrary free fermion theory. And one thing we noticed in this paper here is that this equation can be obtained as the equation of motion from the following action. And this action looks kind of simple, but it's a little bit surprising. So it doesn't only depend on the distribution function f that we care about. It somehow involves a reference state, okay, f0, that I rotate. So the reference state is kind of arbitrary, but that you rotate into your f using this algebra. So it looks like this action depends on this reference state, but its variation doesn't depend on the reference state. It's a little bit like a Wessel-Witten term, this term here. You could write it in one higher dimension and make it only depend on f, but if you want to write it in the dimensions you live in, it has this kind of funny form. And what does all of this mean? So here, here these unitaries are from the group whose algebra is this algebra, okay, so the W infinity algebra, and the trace is the trace over this algebra. The algebra is spanned by functions of x and p, okay? And the trace is integrals over base space. I think it's helpful to remember that so W infinity can be thought of as the limit n goes to infinity of un, in which case you can really just view the trace as trace over un matrices. So if you discretized, if I had a bunch of lattice sites instead of the continuum, this would just be un symmetry, the algebra of these f's, and all of this would just be un. In fact, you can make this correspondence manifest in un in the so-called Etuft basis of these clock and shift, using these clock and shift matrices. So H, the matrix H here shifts things, you can say kind of translates by one, whereas G measures position proportional to the space. So if you take powers of these matrices, that gives you a basis of un. And the commutators of these matrices is exactly this Moyen bracket that we had earlier. Okay, so that makes sense. Manifest the correspondence. So W infinity, this kind of generalization of Poisson brackets is you could say the continuum limit of un. This will be a useful fact because we'll often want to discretize W infinity, go back as we did with our wires. It was useful to discretize the wires in intermediate steps. Okay, so that's the algebra, and then the idea. So you have this action, and what do you do with it? Well, you can use it a little bit like a pion Lagrangian, okay, and like an effective field theory. You can study. So it's a fully nonlinear object, but you could, if you're interested in kind of low energy dynamics, you could expand in fluctuations and study, the correlation functions and so on. So you would do this very similarly to the pion Lagrangian. You write your unitary as exponential of some element of the algebra and expand in phi using the algebra. Okay. So the reference state, you could take it to be anything, but if you want to do perturbation theory, it's going to be useful for it to be the Fermi surface at rest, so the actual expectation value of the fermion twin function, and then you can expand in phi. Okay. Now notice that not any phi leads to a new f, leads to a new independent reference state. Two phis that differ by an alpha that commutes with my reference state clearly are equivalent, right? They'll lead to the same f. So there's some kind of gauge redundancy in this description. And you can use this gauge redundancy to fix phi, to put phi in some canonical form. It's kind of you can mod out by this gauge redundancy. And in practice, what you can do is make phi only have no dependence on the radial momentum p. Okay, so phi started its life as an element of the algebra of W infinity, which is spanned by functions of x and p. But this gauge redundancy tells you that you can remove the p dependencies. So you're left with a field that depends on space-time and angle of the Fermi surface. Let's say in 2 + 1. I could do this in any dimension, but it's nice for drawings to do 2 + 1. So here we're kind of landing on this degree of freedom I had mentioned earlier in Fermi surface bosonization. Okay? This field that depends on space-time and the Fermi surface coordinate. And intuitively, this field represents a particle hole excited near some angle. So now you can expand in fluctuations, use these commutators, like you would for any nonlinear sigma model, except the commutator is a little funny, right? It's this Moyal bracket that has all these gradients. If you do that, these gradients will hit this distribution function, and if you adopt a function localized on the Fermi surface, and then gradients of your phi. You plug this in the action, and what you'll land on to leading order is this Carroll boson at every point of the Fermi surface. Okay? And it will also give you a whole set of nonlinearities. And again, these nonlinearities, their role in life is to produce a nonlinear response. And one thing we checked is that this gives you the expected higher point functions of a Fermi gas. So this action here, this action here was for free fermions. Remember, we derived this abrasion motion for free fermion. arbitrary free fermion Hamiltonian, but now you can, in an effective field theory spirit, we can generalize this to an arbitrary Fermi liquid by just assuming this is the right degree of freedom and writing down the most general action in terms of this distribution function that's local in space, but need not be local in momentum space. Okay. And so the first kind of non-trivial terms, new terms beyond free fermion you can write down are these quadratic terms in F, which would correspond to quartic terms in the fermion language, and they tell you about forward scattering of fermions, and these are the famous Landau parameters of Fermi liquids. But there's of course a whole tower of other irrelevant corrections to Fermi liquid theory that you could add. Good. Okay. But now I'd like to kind of make sense of this description quantum mechanically. So it does a lot of things nicely at a classical level, but we'd like to make sense of this quantum mechanically. So one first comment is that this coadjoint orbit approach in 1+1D completely reproduces what we know about 1+1D bosonization. So if you just take this action in 1+1D and expand, you'll get again a chiral boson, but now there's a single chiral boson. Let's say I have just a chiral Fermi surface, so my distribution function is occupied here and not occupied there. I'll get a single chiral boson, okay? Right from the boson. And if the Hamiltonian, if the dispersion is not exactly linear, you'll get a whole tower of irrelevant corrections to the chiral boson, which are the ones you would indeed expect from conventional bosonization. So this kind of exactly reproduces old work on what's sometimes called beyond Luttinger liquid. Luttinger liquid often refers to the free chiral boson, but there's always going to be irrelevant corrections.
So the choice of the reference state is not important at all, or what you made a choice for the reference state.
No, so when you start doing perturbation theory, it is important because your ground states. If you're studying correlation functions of simple operators in your ground state, in your Fermi surface state, you want fluctuations to be small, right? So if you chose so there, it's actually useful to choose the reference state to be the one whose expectation value F matches. So that otherwise phi would have a large classical expectation value, and you would kind of have to re-expand around there. So it doesn't eventually it's useful to make the right choice. Yeah, it's similar to spontaneous symmetry breaking. You just want to make sure but of course it's nonlinear and it could have been anyway. Good. Okay, so that's good. In 1D, it kind of reproduces known things. I should say for the wire, you can also do this for the wire example that we had earlier. There, I would treat the x direction as continuous, but the y direction as discrete. So you would probably only do the Wigner transform in the x direction, and then your distribution function would be a function of 1D phase space, and would have 2 wire indices, as would phi. Phi would have 2 wire indices. And so the algebra of this object, it lives in W infinity in the x direction. But in the y direction, I discretize, so it really lives in UN. Okay, this is an element of UN. And so if you exponentiate this element of whose algebra is the product of these 2 algebras, this is what it would look like. So it would the point here that's important is that in this x direction, I'm going to expand in gradients. Okay, this W infinity algebra had all these gradients. In the x direction, things cost energy, things disperse. And so I expect a nice derivative expansion in the x direction. But in the y direction, things are completely soft. Okay, so I don't want to write down this Moyal or Poisson bracket and expand in gradients. I want to really treat things exactly. So I want to work with this UN and just not make any approximation on the UN side. And so that's what I did here. I kept the UN structure intact in terms of these G matrices, and expanded in derivatives in these in derivatives in the x direction. And so if you do that, what you land on, starting from this coadjoint orbit action, is exactly the chiral WTW model at level 1. Okay. Plus, of course, a whole tower of irrelevant corrections, depending on what kind of dispersion relation you have for them. So yeah, this makes manifest what I was saying earlier, that this Fermi surface bosonization really kind of looks like non-green bosonization in the soft direction. Okay, very good. So now we'd like to talk about general Fermi surfaces, which can't be reduced, or naively can't be reduced to a one-dimensional problem. So conceptually, I think the idea is fairly clear. We saw that, there's in a general Fermi surface, there's a direction that costs energy, where you kind of expect one-dimensional physics, right? You will expand in derivatives. You'll have things cost energy like usual in particle physics as you go away from the origin or from zero energy states. Then there's this other direction that's completely soft, where the field kind of lives in a non-commutative space. And what we did is that we treated this non-commutativity exactly by representing it as a matrix QFT, right, as a WCW model. So that kind of really captured the non-commutativity exactly. So we'd like to do this in a general Fermi surface, but in a general Fermi surface, it's a mess because as I move along the Fermi surface, the directions that cost energy and that where I have to use capture the non-commutativity exactly are intertwined. So how are we going to do this in practice? So to do this, there's a nice trick that I learned from these nice papers by Ming-Chun and Yu-Xuan, which is to introduce a small magnetic field, which will then take to zero in a little bit. So turning on a magnetic field kind of changes the canonical structure of phase space at a single particle level, and that will be very useful for us. So the individual particles, the gauge invariant momentum is going to be P plus A for individual charged particles. So that the true Fermi surface state is a sharpish, it's a little bit fuzzy because of the field, but a sharpish Fermi surface for the gauge invariant momentum, not for the original momentum, which is not gauge invariant. And what's interesting about this gauge invariant momentum is that it's non-commutative. It doesn't commute with itself, right? The commutators, it forms its own canonical pairs. A commutator K is proportional to B. Another coordinate that's nice is sometimes called the guiding center coordinates from classical particles in a B field, the position of the guiding center, combination of position and gauge invariant momentum. What's nice about this coordinate is that it commutes with K, so it's a completely independent coordinate, but it itself does not commute with itself, so it forms a canonical pair of coordinates. And so this is nice because now we've kind of separated the part. So we used to have X and PX that were pairs, Y and PY, but we separated into two different sets of coordinates that each have their W infinity algebra. And the point is that the energy, the Hamiltonian and the state will only depend on K. Okay, so the part that costs energy is all in this first factor. Whereas the second factor, the Hamiltonian will be completely independent on these guiding center coordinates if you assume the Hamiltonian is translation variant. So this will be a completely soft direction. Okay? So this factor, I'm basically going to treat it like the Y direction for the flat Fermi surface, where I want to do things exactly. I'm going to discretize it and just treat the algebra exactly in this space. Whereas the W infinity knows about weight gauge invariant momentum. There I can kind of do a gradient expansion. I expect gradient expansion to be well behaved because derivatives cost more and more energy in this direction. So this will be the strategy. We'll discretize this factor. To discretize this factor, unlike for the wire case, all you need to do is just put the system in a finite volume, see on a torus. Because of the magnetic field and the fact that these coordinates don't commute, that immediately discretizes it gives you both a UV and an IR cutoff. An IR cutoff in Rx is a UV cutoff in Ry because the two coordinates don't commute, so you can have a discretized spaces. And so and the number of guiding center coordinates will be given by the flux, the total magnetic flux through the torus. This is how we'll discretize the problem. And this number of flux is also the degeneracy of the lambda levels. Okay, so that's basically so now we kind of have this setup. We'll use exactly the same action, and exactly the same steps as before for this slightly modified state. Again, there's a gauge redundancy. You can use it to remove the dependence of phi on radial gauge different momentum. It will only depend now on angle and on this magnetic coordinate. But I discretize this magnetic coordinate, so I'd like to view this as an n by n matrix, okay, similar to in the wire construction. And expand in phi. And what you would find, using exactly the same steps we had before, is that you'll land on a WZW model, but now living in so time, of course, but also in the angle coordinate. So it's a WCW model living in momentum space along the Fermi surface. It has a velocity that's the cyclotron frequency, so related to B field and so on. And this is the form it has. There's going to be some, irrelevant corrections depending on the details of your dispersion and so on, but to leading order is just a WCW. So I claim that this is essentially an exact bosonic description of a Fermi gas in 2+1D. I should say all of this is very 2+1D specific now that I'm using the magnetic field and so on. But that's also where the non-Fermi liquids are expected to be. Most
Are you eventually going to take B to 0?
I'm eventually going to take B to 0. Although I should say this could be also an interesting way to study magnetic field effects in Fermi liquids, but for my purposes, I'm going to take B to 0. So you might worry that there's a bunch of, these. So
what is the large? This will be a large N, but it's something. Look for you. The large N was the magnetic flux. I thought you were going to take that to 0.
Yeah. So I'm going to take volume to infinity first, but interestingly, I won't really need a large N. There won't really be. So you can do calculations exactly in N. In my mind, I want to take volume to infinity first, and so it is kind of the large limit, but
then B to 0.
And then B to 0. But you could ask, oh, what about, what if you kept n phi finite while doing that? And I think you could do that. I think it would be, so the duality is exact, is essentially exact. And you don't need to take large n. And also, the WZW model is solvable for any n. So I don't really need, but I think where it is helpful to take large n is if I want to represent local operators in the original 2+1D space in terms of operators of my CFT. We'll see how we do this in a bit. I think you basically have more resolution when you make n large.
Is this N at all related to the N that, for example, appears in Shankar's description of the Fermi surface? He had some N which wasn't related to the magnetic flux, but it also appeared when you put the here in finite volume.
Yeah.
That was essentially like the angular resolution.
Right. It's kind of related, although if I put if I did this without a field, so basically this N is the number of phase space points that the Fermi surface occupies, but not just momentum space points. So I can't just put a Fermi surface in finite volume and get a certain number of points on the Fermi surface. That's not enough. I need to really discretize phase space along the non-graded direction. But so it's kind of related, but for me, it's important that it's really phase space. It's a phase space. Okay, so the claim is that pre-Fermi gas is equivalent to this theory. Of course, it's a very weird description, right? It lives in momentum space. Regular space is completely hidden in the UN in a way that we'll see in a little bit. So let's test a little bit this claim. For example, let's compute the thermal free energy or the specific heat. This is an observable that kind of guided a lot of our intuition because I was telling you there's this naive overcounting of degrees of freedom. Specific heat is really something that's going to measure how much stuff there is in your system. And it's also a very easy thing to compute. So we have this CFT. It has this cyclotron velocity that can depend on angle, but you could just view it as a CFT on some background spatial metric. And of course, computing the thermal free energy of a 1+1D CFT is extremely easy because mapping to the thermal cylinder is a conformal map. And so we know the stress tensor has some thermal expectation value set by the central charge times temperature to some T squared, and so we can compute the specific heat dissipate. It's going to be the derivative of the energy with respect to temperature. Total energy, so I'm integrating the energy momentum tensor over space. And so this will have this form in the CFT. With central charge given by the central charge of this WZ or chiral WZW model. which knows about volume of the actual space. Okay, so volume is coming in sneakily through the central charge, the actual physical volume. And the answer you land on is indeed reproduces the known specific heat of a Fermi surface of arbitrary shape. So I think it's it's obviously a very old result, but it's kind of a interesting, very unusual way to get there from this only 1 + 1 DCFT. Okay, I have a comment related actually to the question on why I work with this non-abelian description. So this is a bit of a side comment, but I think it's still maybe useful. So in the wire construction, that we have these two descriptions, right? Non-abelian and abelian, both have their advantages, but if you want to do maybe perturbation theory, add irrelevant corrections, you might prefer this, where conformal perturbation theory would be just regular perturbation theory. So you might ask, is there an abelian description of this model? And indeed there is, where the phi's have kind of roughly one less label than you would think. And it's to linear order just going to look like a bunch of chiral bosons along the Fermi surface with irrelevant corrections. Yeah, there's some advantages to this description. And I should say it connects to another old observation, that you can bosonize Landau levels. So if you just take a fermion with k-squared dispersion and put it in a B field, this is the Hamiltonian you will get. You'll have Landau levels that are integer spaced. But this looks a lot like, if you viewed n as px, it looks a lot like the Hamiltonian of a chiral fermion. Okay. And so what these people propose is to just do one debosonization of these, just view this n as space, and so as momentum space. And that so what they obtained actually agrees with the leading firm in this abelianized description. So there's some advantages to both descriptions. Okay, so one motivation was to go beyond this kind of leading answer to do perturbation theory or conformal perturbation theory. You can obviously do this. There will be, if your dispersion relation is not exactly k-squared, that leads to corrections in the movement description, which just corresponds to irrelevant operators in the CFT. And these will lead to corrections to the thermal free energy. So you can compute this straightforwardly, and this matches also what you would expect from the fermion perspective. You can also look at local observables, and those are a little more interesting because, so local observables in real space that we started with will map to some kind of we'll map to operators, to local operators in the CFT, which live in momentum space. And so there's some map that you can figure out, which looks a little funny. So for example, the density operator is going to be related to the current of the CFT, WCW CFT, through, times some kernel that kind of interweaves these real space coordinates and this momentum space coordinate. And there's, of course, going to be a whole tower of corrections to this. And you can use this to study, so we check that it reproduces corrections to correlation functions that you would expect. And yeah, so this is again, I should say this tree level piece you could get without all of this work. But as soon as you start looking at these conformal perturbation theory corrections, you really need to know you need the full quantumness of the WCW model to capture these corrections. Okay, so let me summarize what we have so far. So I've argued that a specific UN level 1 WCW model living on the Fermi surface corresponds essentially exactly to a 2D free Fermi gas. This is a description that makes the semi-classical limit manifest, and it can be one can use it quantitatively using conformal perturbation theory to study low energy physics. But so far, I've kind of only been reproducing free fermion observables. So I'm doing a huge amount of work on the boson side to do things that are almost trivial on the fermion side. Can we do anything new with this? So the point of bosonization is that, of course, maybe while free fermions might be complicated, the adding interactions should be much simpler, and that is indeed the case. So if now you want to consider an interacting Fermi liquid, you can think about deformations of the this field theory, this kind of CFT that we had, that corresponds to the leading interactions of the Fermi liquid. Okay. And so in the semi-classical picture, these are the leading deformations I mentioned earlier that to Fermi liquid theory that have a bunch of interesting consequences. So if you expand this in the Bosonized description, what's interesting is that it's Gaussian. It's going to be a pi squared term. Okay. So while this is a 4 Fermi term in the fermion description, it's Gaussian in the boson description, so it's easy to deal with. And it leads to a lot of interesting things like new collective excitations, zero sound, and so on above the particle boson. So it has some interesting physics, which of course is well known, but it also has qualitatively new nonlinear terms whose role is to precisely produce this multi-particle hole continuum we had earlier, right? It's opening up these whole new states. And so this is a diagram, right, which is basically just kind of a one loop-like diagram in this Bosonized description, but would be a 3-loop diagram in the fermion picture, and it's extremely difficult to compute because of the partial cancellations I mentioned earlier. But it's easier to deal with on the boson side. So right. At least it's easier to guess the scaling of this diagram. So this will be a diagram a bit beyond those that we computed so far. We have these first diagrams that correspond to pre-Fermi gas, but now we're considering extra ones coming from interactions in the action. And it turns out that these diagrams are actually even simpler to compute than the free fermion ones we had over here, because essentially the non-perturbative WZW model physics is unimportant for these diagrams. And I think the intuition for it is that these Landau interactions are coupling 2 different patches of the Fermi surfaces. And the non-commutative directions of these 2 patches are not aligned. And so it actually makes these loops much better behaved because all directions now cost energy, for these particles. This direction costs energy for this direction costs energy. And so you end up, you can actually expand in fields. It becomes, the model kind of becomes perturbative. These diagrams are perturbative for some reason. So you can really just expand in this phi field. And because of this, getting the scaling of these effects is very simple.
Sorry, what is that for some reason?
For some reason. So yeah, let's see. So in the sense that you're not happy with the intuitive explanation, or
well, I thought for some reason it means it's unobvious
that it should have happened. Yeah. No, maybe in retrospect it's obvious. So you could. There's a puzzle which I don't completely know the answer to. So there's this field theory which looks a little bit funny. I've given you a full quantum definition for it, so you could certainly use that in computer everything. It's a little bit complicated. And you might ask, when can I just there were all these nice tree level diagrams where I got the right answer. Okay, I had this e to the phi everywhere. I expanded in phi, got the right answer, even though I'm telling you, it's a strongly coupled WZW model. Sometimes the kind of classical expansion gives the right answer. And I don't have a very good intuition for why, but I think there's something deep to it. So there's some observables, which there's some physics behind it. There's some observables that are basically dominated by effects by intermediate states that basically only care about forward scattering, whereas some other observables care about head-on collisions. So head-on. Okay, maybe this is getting a little bit into details, but there's some phenomena that are just kind of lost in this semi-classical description. So it certainly didn't have to work. But for some observables, it does, because these intermediate states are not important, are not the dominating mechanism.
What's an example
where
which is lost semi-classically?
Right. Well, okay. I mean, no. So so for example, the specific heat, it gets completely wrong, right? Because you just have n squared degrees. Yeah. So there's, and that would be kind of a one loop, effect that doesn't couple patches. Okay, unlike this one that. And similarly, in these corrections, so these were 3 Fermi gas corrections, which came from but they were all on the same patch roughly. The free-forming gas is kind of local in patch in momentum space. It didn't have to be, but the free-forming gas is. And that is it's kind of really sensitive to this. So these loops are highly non-perturbative. I wrote them as loops, but they're kind of highly non-perturbative. They really require the whole WZW, reduction of degrees of freedom. Whereas these loops that couple different patches are perturbative. So yeah, I think in this specific example, I understand why one is and one isn't. But more generally, if you give me an observable, knowing beforehand when I can, using the model should also always work. But knowing beforehand when I can cheat and expand, I don't have a super good intuition. That's an excellent question. But so when you can expand, there's a very simple, scaling argument for how big.
All related to how things scale with n.
How things scale with n. Yeah. You're saying because the specific heat is an example where it's n squared versus n. Right. Yeah, there might be that certainly gives a hint because if you look at a local observables, you don't expect powers of volume to show it because n knows about volume. So that might be a way to guess beforehand. Yeah. Right. So when when you can expand, you can really kind of treat it as conventional effective field theory. There's a nice power counting argument. You could figure out how the field scales, and that will tell you how irrelevant interactions are. It's interesting to contrast the kind of charge response that I've been talking about to flavor. If you have several flavors of fermions or spins, right, like the spin of the electron, that changes. So there you would have the Bosonized degree of freedom would have more indices, for example, here for SU2. And the interactions have fewer derivatives, which leads to less suppressed nonlinearities in this context. In this context, cubic nonlinearities are a little bit less irrelevant. And so the loop corrections requires two of these nonlinearities, and so it has this power of Q compared to the leading term. And this was actually known from the fermion description. So it's a specific free loop diagram that you compute, and people had computed it and found this power law. And they had also computed it in the charge sector and found zero. And so all of this will be obvious. It's obvious from the fact that there's more derivatives here. In fact, what we can see here is that if they had gone one higher order, they would have still found zero, and that the first non-zero term is at this higher order. So it kind of streamlines these calculations. Okay, let me try to conclude. So I kind of showed you that bosonization makes some perturbative studies of Fermi liquids more tractable. My hope is that it might be able to push this to non-Fermi liquids. I think there's still a bunch of kind of interesting open questions. Maybe I'll briefly comment on this point because this is a kind of nice UVIR constraint that we studied in this paper, which is you might ask, what constraints do I have on a Fermi liquid if I obtain it from a CFT? If I take a CFT with a U1 symmetry and I turn on a chemical potential, does that constrain in any way the Boltzmann coefficients of the effective field theory? It's a bit subtle because the symmetries of the CFT are non-linearly realized on the effective field theory, but there are constraints. And they're kind of generalizations of these old Landau relations. So Landau had studied the case of Galilean invariance, where the first Landau parameter is fixed in terms of other EFT coefficients. Similarly, Lorentz invariance also fixes this first. So boost kind of fixes the first Landau parameter. But scale invariance leads to a similar constraint on the zeroth Landau parameter in terms of other coefficients of the CFT. There's other interesting kind of causality constraints on these parameters that we studied. Okay, very good. So I think I'm out of time. Thanks a lot for your questions. Then I'll take some more now.
What CFTs have you Fermi liquids?
So there are examples. So Fermi liquid, it's not the most stable finite density state of matter, right? A superfluid is much more stable. Fermi liquid almost always has the BCS instability, but often there's a big window of stability. So there are examples where large N Chern-Simons matter theories, where thanks to large N, it's actually stabilized and it's the true ground state.
Stabilized in the sense of maybe the gap is e to the minus n, BCS gap and e to the minus n.
Right. Yeah. So that right. There's some non-commutative low energy. Right. So there would be a huge window. Yeah. So it's a marginally relevant interaction. So that even there'll still even if it's not the exact ground states, that's why it's relevant in so many experiments. Right? There's this huge temperature range where it still matters. But that's an interesting example because the Landau parameter is order. So there's this Tuft coupling k over n in the Chern-Simons matter theories, and one of the Landau parameters is basically that Tuft coupling, so you can really tune across the moduli space, part of the moduli space of Fermi liquids in these models. And and there's definitely some CFTs that should flow to non-Fermi liquids because, well, actually that model, so that model has gauge fields and fermions and a Fermi surface. But thanks to the large N, they don't interact too much. So that's why you have a stabilized Fermi liquid. But the leading 1/n effect looks like something that would lead to non-Fermi liquid physics. So yeah, But if you want, right? But there are other examples of weakly coupled CFTs that flow to Fermi liquids, at least for some range of temperature.
Maybe follow up a little bit on you mentioned something before at lunch about what the PCS interaction would look like in this time.
Right. Yeah. So here there's a kind of complete dictionary between operators you care about on the fermion side and how to write them in the WZW model. So in particular, a fermion bilinear. So yeah, a fermion bilinear that involves two different points of in theta will correspond to the BCS interaction has side dagger, side, right? It's a kind of head-on collision into another. So this involves two different angles, well, theta plus pi, and then theta prime plus pi. So this will map. I mean, basically, let's see if I have an equation. Yeah, I have an equation here. Roughly an equation of this form, right? Where you give me the fermion operator you're interested in, and that's going to have some representations in terms of G, and I can add this to the action. In the abelianized form, it would literally be a vertex operator with charge 2. So that would be the side dagger, right? It would be just the charge 2 vertex operator. So now, right, so that's something that was not possible to do with this kind of classical action. Now we can actually add this to the action and ask, see its effects, ideally reproduce the fact that it's marginally relevant. Although we haven't tried this yet.
Other questions? All right. Thanks, Luca.